We're asked for the rate of change of the area of the triangle. So the area of a triangle is 1/2 times the length times, the base times the height. Let's do a rectangle. Right? The area of a triangle is 1/2 times two things that make a right angle with each other in the triangle. The base times the height. So we're supposed to find the rate of change of the area. So we want A prime. And then it's the derivative here. Let me actually write this in more explicit notation. We want the derivative of the area with respect to our variable time here. This triangle is shrinking according to, depending on the amount of seconds that have passed, according to that first sentence. So what that means is we got a triangle. It's a certain centimeters in length, but then if you go 1 second later, it's decreased. Here, if this is the length, then it's the length minus 11. The triangle is shrinking. It's the length minus 11. It's decreased by 11 centimeters 1 second later, and then another 11 centimeters, and then another 11 centimeters. So that's what the related rates problem means, in the context of a triangle. So if we're trying to find how fast the area is changing, because look, if you shrink that length by 11 centimeters, you made the triangle more narrow, there's less area, right? So the rate of change of the area with respect to time, it should be negative. The area should be decreasing. Okay. So we're taking a derivative of the area with respect to time in terms of seconds. And so to do that, we need implicit differentiation, because whatever the base is in terms of seconds, we don't have a formula for that. We don't know what the height is after a certain amount of seconds. So both of those are unknown variables when we talk about the base and the height in terms of time. So we have to use implicit differentiation. This is one function of s, and this is a different function of s. So that's the product rule for differentiation. It's the derivative of the first function with respect to time times the second function kept the same, plus the original first function times a derivative of the second function with respect to time. So you have to use both implicit differentiation and the product rule here, because those are two distinct functions. And it says, what is the rate of change of the area of the triangle if the height is 9 centimeters? So that means h is 9. And then they also tell us the triangle has a base that is decreasing at a rate of 11 centimeters. So that means the rate of change of the base with respect to time is negative 11, because we said it's decreasing, right? I think we have enough information to plug in. Actually, we don't have here. Rate of change of the area with respect to time. The height is 9 centimeters. Oh, it says the height is being held constant. That's the other important piece, because I was thinking we have this. They told us the rate of change of the base with respect to time is negative 11. They didn't tell us anything about the rate of change of the height with respect to time until I read this part. The height is being held constant. So the rate of change of the height with respect to time is 0. Okay, the height is held constant. Now we have enough information to plug in to find dA, ds, to find the derivative of the area with respect to time. dB ds, we said, is negative 11. The height is 9. And then this whole thing doesn't matter what the base is. They don't even tell us. Doesn't matter, though, because it's changing at a rate of 0 centimeters per second. So if you simplify, that's negative 99 over 2. So it's negative just like we expected. And then after we plug in the information, the area is changing at a rate of negative 99 over 2 centimeters. And that would be squared, right? Because area is two-dimensional. We're supposed to find the rate at which the area of a circle is increasing. And it looks like time is the underlying variable. So they want dA dt. We can just shorten it and call it A prime when we're working on it too. So we have an equation for the area of a circle. That's where we want to start, because that's how we're going to be able to get an A prime. We're going to differentiate it with respect to time using implicit differentiation. Nerdiest thing I've said all day, hopefully. But the area of a circle is pi r squared. So if you take a derivative of both sides with respect to time, the area with respect to time is something unknown, so we would leave that as A prime. And now pi is a constant, so don't use the product rule here. The 2 comes down and multiplies. But then we need a derivative of the innermost function, right? The power rule applies for the outermost function, but then the derivative of r isn't 1. It's r prime. If we were taking a derivative with respect to r, if we were doing ddr, then this would just be 2 pi r for a derivative. But since we're taking a derivative with respect to time everywhere, we don't know what r is as a function of time, so we have to leave it as r prime. Okay, so they tell us the radius of the circle is increasing. So r prime is positive 11 because it's increasing. We're supposed to find the rate at which the area of the circle is increasing when the radius is 8. So r is at 8. So plug in 8 for that. Plug in 11 for that. And then things in terms of pi. So we got 88 times 2. What is that? Man, I'm so bad with math. That's 176 pi.